Hello, my name is Mark Allspaw, the president of Overland Conveyor Company. I'd like to welcome you to Module 1 of our Belt Conveyor Engineering Software webcast. Today we're going to do an introduction to belt analysts. Overland Conveyor Company is a consulting engineering company that specializes in belt conveyor design engineering and technical support. We are also a software developer and marketer. We specialize in belt conveyor engineering software. Our main product is Belt Analyst, which we'll be talking about today. We also have Dynamic Analyst, Horizontal Curve Analyst, Pipe Conveyors, Unit Analyst. We have some proprietary products such as the Mezzo Cable Belt and the Doppelmayr Rope Con. We also do custom programming, and we do private branding for particular customers. We also have discrete element modeling software packages named Bulk Flow Analyst and Chute Analyst, which will be covered in later presentations. Today we're going to talk about Belt Analyst, which is our base product for belt conveyor design. All the belt conveyor software developed by Overland Conveyor is designed and written by belt conveyor engineers. We actually use these exact same programs for our own consulting work, and we do consulting on some of the biggest and most complex major conveyor systems being designed and constructed in the world. Belt Analyst was first developed in 1996 and is used by thousands of people around the world today. Belt Analyst is in continuous development. We have multiple programmers developing all the time. We introduce one major upgrade per year with significant new features, and we have multiple smaller upgrades each year to fix problems and to add smaller features. Belt Analyst is a static design program. It uses one of three different methodologies. The SEMA, which is the Conveyor Equipment Manufacturers Association of North America, has two different methodologies, the 5th edition and a new universal method in the 6th edition. We also have the DIN 22101 German standard and ISO International Standards methods. Belt Analyst can be used to design conveyors up to, has been used to design conveyors up to 30 kilometers long, but there is no limitation to the length it can be used. It can be used on belt widths up to 3.2 meters, 360 segments, 48 pulleys, 20 drives with unlimited power, and belts strengths up to ST10,000. You can see additional training videos on our temporary e-training site, which is located at overlandconveyor.com/training/trainingvideos.html. This will be expanded over time and will include a tremendous amount of material. So go back to this site periodically and see what's new. Now for the next few minutes we're going to go over the basics of the program. The screen is divided up into a couple of different pieces with several graphics here on the right side of the screen, including a cross-sectional area, profile, a simplified profile of the conveyor, tension diagram. On the left side of the screen we have component tabs with a lot of specialized data. Up here across the top, just like any Microsoft program, we have the menu buttons for opening and saving files, printing, changing units, help files, all the regular stuff that comes in a Microsoft program. So down the left side of the screen we see a series of tabs here that open up dialog boxes and grids. And basically goes through all the different components that we'll address here in a little bit. The cross-sectional area of the conveyor, including the carry and return idler, troughing idlers, the belt, and the cross-sectional loading, and shows it for both the carry and return. Right under that we have our what we consider to be sort of our cartoon or our simplified profile. The left side of the screen is the tail, the right side is the discharge, and below that is our tension diagram. Our tension diagram gives us a lot of information. Starts off with the tension in the belt at the exit of the tail pulley. The tension in the belt increases as it goes from left to right across the screen or from the tail to the head of the conveyor. The tension in the belt decreases as it goes around the drive pulley, and then the tension goes back to the return side, and the right side of the tension diagram matches up with the left side. So we simply break the belt and stretch it out to look at the tensions in a complete tension cycle. If we take a look at this a little closer, we're going to delete the actual blue and pink lines and just look at the running tension diagram in the belt. The black line represents the running conditions, the steady state running conditions. The solid gray line right here is the rating of the belt. Put a little mark on that. That's the rating of the belt that's selected in this particular snapshot. There's the 75 newtons per millimeter rating of the belt. The dotted gray line along the bottom is the minimum sag tension in the belt. We have to make sure that the belt tension doesn't get too low so that the belt would sag too much and spill material, just as much as we want to make sure that the belt tension doesn't exceed the rating of the belt. I'm going to go up here and click on the starting tension diagram and add the blue line, which represents the acceleration tensions as we start the conveyor. This is an approximation of acceleration using rigid body mechanics. And I'll click on the button that turns on the stopping or drift tensions, which is the pink line. So now we have running, starting, and stopping tensions all plotted on a single tension diagram. And the idea is we want to keep our tensions within the minimum and maximum limits of the components we've selected. Next thing I want to talk about here is color coding that we use for the inputs and outputs. Anytime you see a black number, which I've highlighted there under drift time, and we'll actually highlight here in the belt tab, anytime you see a black number, that's a calculation, and it can't be changed by the user, so that's all output and not input. The blue numbers are our input information. For instance, we can input, the user can input the top bottom cover gauges. Over here, if you can see this, the blue numbers, all the belt width and speed and tons per hour, load capacity is all blue. If there's two different types of blue numbers. If there's a dark blue and a light blue, or a regular blue and a bold blue. The bold blue or dark blue means it's an input that the user has put in and will not change unless the user changes it. The light blue represents a potential variable that a user can change, but in this case it's been calculated by the computer. Acceleration time and torque is a good example. You always put one value in and it calculates the other. Since the 145% starting torque is in bold blue, we know it's been input and the acceleration time calculated. If we input a 21-second acceleration time, you see it turns bold blue, and the torque, the resulting calculated torque, turns light blue. And if I put in 120% torque, you see just the opposite. The acceleration time turns light blue. So any blue variable can be changed. Light blue represents, it means the computer has calculated it or picked it out of a database, and dark blue means the user's input it. If you'll notice here, there's a bar that goes across the screen every time we change one of these variables, this green bar. We're in auto calculate mode, which is one of the features of our program. Anytime you change any variable in the program, everything will be recalculated. All the belt tensions, all the pulley loads, all the idler loads, every piece of information will be recalculated, every time we change any variable when we are in auto calculate mode. We can switch out of auto calculate into manual calculate by pressing this button at the top. We click it into manual calculate, then we have to hit F9 to recalculate. If we click it again, you see it goes back into auto calc mode, which is where we generally like to leave the program.